Hello, class. Recall that the Black-Scholes-Merton fundamental partial differential equation has this particular form here for a derivative product where the underlying asset uh, follows the log normal process and has no dividend payment. Now, this being a fundamental partial differential equation means like that any derivative product, as long as it is a derivative product with underlying asset that follows the log normal process and pays no dividend, must satisfy this equation, no matter that derivative product is a call, a put, or any other products. So let's take a look at whether that is the case, because it should be the case. Then let's try to convince ourselves that actually, what we just claimed is really what we should derive and should obtain. Now, if you look at the pricing formula, the closed form formula for a call, which has this particular form, this is the Black-Scholes formula for call, and we claim that this is a solution to that fundamental partial differential equation. So by definition, this should satisfy that equation, okay? And also here we have a forward contract, which should have a pricing formula of this form. Now, if this is the right pricing formula for a forward contract on a stock that follows the log normal process and pays no dividend, this pricing formula for the forward contract should also satisfy the fundamental partial differential equation. Okay, let's see whether that's the case. When you look at the call here, the this part here is the left-hand side of the fundamental partial differential equation. So it's basically theta plus r times s times delta plus half of gamma times sigma square s square. So you plug in those values or those expressions that we have seen earlier. So you get a theta here and r times s times the delta and one half times gamma times sigma square s square, okay? And rearrange where, there's an R here, there's an R here, collect the terms, you have this. And the other terms are collected here. Now you see that S sigma is there's a sigma square S square here, so you're left with the sigma times S. So basically, these two terms will cancel one another. And what you can recognize here is that this SND1 minus K times e to the power of minus RT and D2 is just F. So this becomes RF. Basically, the left-hand side is equal to this expression of the right-hand side, which is exactly this fundamental partial differential equation. So we show that the call price here satisfies this fundamental partial differential equation. So that means it's the right call price. Now, for forward contract, we have this form, and this is relatively easy. So if you take the theta there, you will get minus r times k times e to the power of minus rt. Here, dfds is just 1, and there's no second partial. So if you plug in the expression to the left-hand side of the fundamental partial differential equation, you get this thing plus rs, that's all. And if you collect the terms of r, you will, what's in the bracket will be s minus k times e to the power of minus rt, which is just this. So you also have r times s. So this part here is equal to RF. So again, this shows that this particular for the pricing formula for the forward contract that we written down here is that this formula satisfies the fundamental partial differential equation. You can use an treat it as an exercise where you can try to show that the put formula also satisfies the fundamental partial differential equation. Now, in many cases, when we try to solve the this fundamental partial differential equation to obtain a particular pricing formula, it's difficult to actually solve it directly. But from experience, there are many forms that people would, can as intuitively tell us that that could be a particular solution. So the solution of this equation may likely take a particular form. And then you can try that particular form. And if that form satisfies this equation, then you have a way to show that that pricing formula, the one you guessed, the pricing formula taking a particular form actually is the right pricing formula. So we will see those kind of cases later on in this course. So it's important to be able to show that a particular pricing formula satisfied the fundamental partial differential equation. It's an important check.